So far in our rate law, we have not seen any indication that temperature plays a factor. There's no temperature in our rate law equation. However, it's pretty universal knowledge that as we increase the temperature, our reactions happen at a faster rate. So where does the temperature come into play? Well, the temperature comes into play in our rate constant. So the rate constant K is actually a larger equation in itself that includes a frequency factor, an exponential factor, which also includes our activation energy and temperature. So T is our temperature in Kelvin, R is our gas constant, and we need to use the gas constant with units of joules because our activation energy is going to have units of joules. And we have something called the frequency factor, and the frequency factor is the rate that our reactants are gaining energy to try and overcome that activation energy. So our temperature all comes into play in that in that rate constant. All right, so when we look at chemical reactions, you'll frequently see diagrams that look like this, where we have the energy of our reactants on the left side and the energy of the products on the right side. So in this case, this would be an exothermic reaction because the energy of our products are lower than the energy of the reactants. That hump in the middle, that is what we refer to as our activation energy. So we have to add a specific amount of energy in order to get our reactants to form the products. So let's look at a simple reaction. We're going to look at our methylisonitrile turning into acetonitrile. And what is happening is we're just flipping the nitrogen and the carbon around in the molecule. So in order to do that, we actually need to weaken the bond between the carbon and the nitrogen so that this CN group can rotate. So when we do that, as our reaction begins, we have to weaken that bond enough for the carbon-nitrogen to start rotating on the molecule. And when it rotates, so when it becomes perpendicular, so that the carbon can grab on to the other carbon instead of the nitrogen, this is what we refer to as the activated complex, or sometimes you'll see it called the transition state. And so it's a chemical species where there are partial bonds that are present. And then as it goes past that activated complex, past the transition state, it becomes the products. And our hump in the middle is our activation energy required, so the amount of energy we need to put in order to make that activated complex. In this case, in order to weaken the carbon-nitrogen bond and rotate the CN part of the molecule. So our activation energy is the difference in energy between the reactants and our activated complex. And the frequency factor is the number of molecules that start traveling up this slope. So the more molecules that have enough energy to start traveling up the slope towards the activation energy, the higher our frequency factor in a given amount of time. And so if we increase our temperature, we're going to have more energy in our reaction, and more of them are going to be able to travel up that slope and eventually form our activated complex. So the frequency factor represents the number of times we approach that slope in order to overcome our activation energy. And it is per unit of time, so it is a rate that is happening. In this particular example, you can think of it as the NC molecule as it begins to rotate. You can think of it kind of like a dog's tail wagging. So as it begins to weaken that bond and begin to rotate, it's wagging back and forth. And that's what our frequency factor represents in this particular example. So the amount of times that that bond weakens and it approaches that activation energy barrier. So these are all pieces that affect our rate constant. So our temperature, our frequency factor, the activation energy, all play a part in that rate constant. If we look at the entirety of the exponential factor, so e to the negative activation energy over RT, this results in a number somewhere between 0 and 1. And it's basically telling us a fraction of our reactant molecules that will have enough energy to get over that activation energy barrier. Now, different reactions do have different amounts of activation energy required. So if it's a higher barrier, there's going to be fewer molecules that can get over that activation energy barrier. If it has a lower activation energy, then more of our molecules will be closer to a value of 1. If we increase the temperature, that adds energy into our reaction and increases the number of molecules that can overcome the activation energy. So increasing our temperature will increase the rate of our chemical reaction. If we take the natural log of the rate constant equation, also known as the Arrhenius equation, we can find that we get a linear relationship between the natural log of K and 1 over the temperature. And when we solve it this way, our slope becomes equal to negative activation energy over the ideal gas constant, R. Again, remember that is the 8.314. And our intercept becomes the natural log of A. And so we can solve this to find our activation energy in joules by taking the opposite of the ideal gas constant times the slope of our line, and we can find our frequency factor A by taking the the y-intercept and raise it to the power, or e to the power of our y-intercept. And this will give us the same units as K. So our frequency factor is measured in the same units that K has. So let's look at an example. Let's determine the activation energy and the frequency factor if we're measuring ozone decomposing into oxygen and free radical. So we're given the following data. We need to manipulate it. So we're going to have to convert our temperature to 1 over the temperature, and K is going to have to take the natural log of K. When we do that and we plot it, we can determine our equation of the line. So we have the slope and we have the y-intercept. So to find, remember our slope is negative EA over R. So if we want to find Our activation energy, we're going to have to take and rearrange this. Take negative R, which is 8.314 joules per mole Kelvin, times our slope, negative 1.12 times 10 to the 4th Kelvin. Our kelvins cancel. That will equal our activation energy, and we get 9.31 times 10 to the 4th joules per mole for our activation energy. If we want to convert that into kilojoules, we divide by 1,000, and we get 93.1 kilojoules per mole for the activation energy of this particular reaction. If we want to find our frequency factor, we're going to take E to the intercept, which in this case is 26.8. And we see that we get 4.36 times 10 to the 11th. And so the units on that are going to be the same as what our units on the rate constant, which is 1 over molarity times seconds. So we can find both the activation energy and our frequency factor by plotting the data as the natural log of our constant and 1 over the temperature in Kelvin.